In the boundless cosmos, our solar system is not a completely enclosed garden. It is constantly bathed in the breeze of interstellar matter. Occasionally, distant visitors intrude. Throughout humanity's long history of astronomical observation, we have always assumed the existence of these interstellar visitors. But it was only in recent years that we truly confirmed them. The first interstellar object discovered was Oumuamua. It was captured by the Pan-STARRS telescope in Hawaii in October 2017. Oumuamua's shape was elongated, resembling a cigar. Its trajectory clearly indicated it originated beyond our solar system. This discovery thrilled the astronomical community, as it offered a rare opportunity to study extraterrestrial matter directly. However, Oumuamua was very small, possibly only a few hundred meters long, and was already on its way out of the solar system when discovered. Many critical observations could not be conducted, leaving scientists with numerous unresolved mysteries. Just 2 years later, in August 2019, amateur astronomer Gennady Borisov discovered a second interstellar visitor. This comet, named Borisov, displayed a distinct coma and tail. Its behavior more closely resembled familiar solar system comets. Yet it too followed a hyperbolic trajectory, confirming its origin in distant, alien worlds. Borisov's discovery proved Oumuamua was no fluke. Interstellar objects are indeed continuously crossing our home turf. This opens a new chapter in our understanding of planetary system formation and evolution. Against this backdrop, the third confirmed interstellar visitor quietly emerged. Its name, 3I Atlas. Here, 3I denotes the third interstellar object, while Atlas refers to the survey project that first detected it. On a seemingly ordinary night in July 2025, telescopes in Hawaii captured a faint speck of light, located in the direction of Pegasus. At the time, it was approximately 420 million kilometers from Earth. Its brightness was extremely faint and could only be observed through large telescopes. The initial data did not immediately cause a sensation. Astronomers recorded its position and brightness following standard procedures. However, over the subsequent nights, continuous observations revealed a startling fact. This object was moving at an extremely high speed. Furthermore, its orbital calculations indicated a highly eccentric hyperbolic trajectory. A hyperbolic orbit signifies that this object was not bound by the sun's gravitational pull. It was merely a fleeting visitor to our solar system, originally from interstellar space and destined to return there. This discovery instantly thrust 3I Atlas into the global astronomical spotlight, for it was not only the third interstellar visitor, but preliminary data indicated it was significantly larger than the previous two. In the days that followed, observatories worldwide trained their telescopes upon it. Chile's Very Large Telescope, the United States Steward Observatory, and the Earth-orbiting Hubble Space Telescope all joined the observation effort. These early observations aimed to determine 3I Atlas's fundamental properties. Its brightness fluctuations suggested it might be an active object, with surface ice sublimating under solar heating, forming a thin cloud of gas and dust, the coma. Spectral analysis revealed a low surface albedo and a reddish hue. This could indicate the presence of complex organic molecules on its surface. These initial characteristics led astronomers to classify 3I Atlas as an interstellar comet, similar to Borisov but distinct from the metal rock composition of Oumuamua. However, as more data accumulated, scientists soon realized 3I Atlas was no ordinary comet. It exhibited distinctiveness in multiple aspects. First, its absolute brightness far exceeded expectations, suggesting its nucleus size might be significantly larger than previously estimated. Second, Its orbital plane aligns almost perfectly with the plane of the solar system's planetary orbits, a coincidence with extremely low probability. Finally, its spectrum revealed unusual chemical signatures. These traits defied explanation by standard cometary models. The discovery of 3I Atlas heralded a new epoch in astronomy. We no longer stumbled upon interstellar visitors by chance, but began systematically studying them, realizing they might possess remarkably diverse forms and properties. From the slender Oumuamua to the comet-like Borisov, to the massive and anomalous 3I Atlas, each reveals distinct secrets of distant star systems. As the largest and strangest interstellar visitor known at the time, 3I Atlas was destined to rewrite our understanding of interstellar space. The story has only just begun, yet it already heralds an impending revolution in astronomy. Weighing distant celestial bodies in the cosmos remains an eternal challenge for astronomers. We cannot directly touch these objects, but the laws of physics provide us with an invisible scale. One of the core principles of this scale is estimating mass by observing non-gravitational acceleration. To understand this ingenious method, we must first grasp the behavior of comets. As a comet approaches the sun's radiant heat causes ice on its surface to sublimate directly into gas. These gases eject from the comet's nucleus, like countless miniature rocket engines. This outflow generates a subtle thrust that continuously acts upon the nucleus itself. The additional acceleration imparted by this thrust exceeds the effect of solar gravity alone, and is thus termed non-gravitational acceleration. This presence subtly alters the comet's orbit, causing it to deviate from the path calculated by pure gravity. Astronomers can precisely measure the magnitude of this orbital deviation by meticulously tracking a comet's position over extended periods. This allows them to infer the strength of the non-gravitational acceleration, and thereby estimate the approximate mass of the nucleus. The more gas an active comet releases, the greater the thrust it generates. However, if the nucleus itself is very small, this thrust can easily propel it into a noticeable deviation from its orbit. Conversely, if the nucleus is extremely massive, even intense gas outflows will cause only a negligible change to its orbit, making it difficult to detect. This is the theoretical basis for weighing 3I Atlas. When observatories worldwide focused their attention on this interstellar visitor, they quickly discovered a puzzling phenomenon. 3I Atlas exhibited clear gas release activity. Its coma was distinctly visible. Spectrometers also detected volatiles like water ice and carbon monoxide, confirming it as an active comet. Yet, ultra-precise measurements of its orbit revealed its trajectory aligned almost perfectly with predictions from a pure gravitational model. The upper limit for non-gravitational acceleration was constrained to less than 15 meters per second squared per day. This value was exceptionally small. For a celestial body so active and continuously releasing gas, what did this stark contrast signify? Scientists immediately envisioned the only plausible explanation. The object's mass must be extraordinarily large, so immense that the thrust generated by its surface gas jets would be akin to attempting to propel an aircraft carrier with a garden hose. The force certainly existed, but it was utterly incapable of inducing any observable motion in this colossal object. To transform this intuition into definitive scientific data, the research team conducted a series of rigorous calculations, utilizing key observational data from the James Webb Space Telescope, which measured 3I Atlas's gas escape rate at approximately 150 kilograms per second on August 6, 2025, a remarkably high outflow rate. combined with nearly negligible non-gravitational acceleration. Researchers constructed mathematical models to calculate the minimum mass required for an object to resist the thrust of such a gas jet. The final calculation stunned everyone. 3I Atlas's minimum mass was a staggering 3.3 billion tons. This figure may seem abstract, but we can grasp its significance through comparison. The famous Halley's Comet in our solar system is estimated to have a mass of about 300 million tons. Thus, 3I Atlas's mass is at least 10 times greater. Compared to previous interstellar visitors, this disparity reaches astronomical proportions. The first interstellar object, Oumuamua, had an estimated mass of merely a few million tons. The second interstellar comet, Borisov, also fell within the tens of millions of tons range. Yet 3I Atlas's mass is thousands to tens of thousands of times greater than Oumuamua, and hundreds of times greater than Borisov. Such a massive difference is not merely quantitative, but likely signifies a qualitative leap. The size and mass distribution of celestial bodies in the universe typically follows a pattern known as the power law distribution. Simply put, small bodies are extremely common, while large bodies are exceptionally rare. For instance, within our solar system's asteroid belt, countless pebbles and sand grains exist, but large bodies like Ceres, with diameters of hundreds of kilometers, are few and far between. Based on the most advanced planetary formation models available today, it is possible to estimate the frequency of interstellar objects of different sizes appearing in the Milky Way. For colossal objects like 3I Atlas, which may reach diameters of 5 to 10 kilometers, theoretical predictions suggest they traverse the solar system roughly once every 1,000 years or even less frequently. Yet, within just a decade of systematic human searches for interstellar objects, such a rare, massive sample has been discovered. This is statistically highly unusual. Harvard astronomer Professor Avi Loeb has termed this the mass budget puzzle. He contends that existing models of cosmic matter density struggle to explain why we would encounter such a massive interstellar object so rapidly, unless our models contain fundamental errors, or 3I Atlas itself is not an ordinary natural celestial body. This exceptionally large mass estimate compels scientists to consider more radical possibilities. If 3I Atlas is not a solid rock and ice sphere, but rather an object with a complex internal structure, such as a hollow shell or a porous structure, it could entirely maintain its immense size, while possessing the observed 3.3 billion ton mass. A spherical shell with a diameter of 10 kilometers, even with a shell thickness of hundreds of meters, could potentially have a total mass consistent with the estimate. Such a structure is highly unusual for a naturally formed celestial body. But for some kind of technological artifact, it represents a reasonable engineering design, achieving strength through geometric structure rather than material accumulation, much like the ships, aircraft, and spacecraft we humans construct. Of course, no direct evidence currently exists to confirm 3I Atlas is hollow. All our inferences are based on dynamic measurements. Yet this immense mass itself stands like an open door, inviting us to contemplate explanations beyond conventional frameworks. The enigma of 3I Atlas's mass is not merely a dispute over a number. It profoundly challenges our understanding of interstellar material composition, compels us to question what manner of objects actually drift through the vastness of interstellar space, and where will the boundaries of humanity's cosmic imagination. Our solar system is a relatively flat structure. All 8 planets orbit within an approximate plane known as the ecliptic plane. This plane is a relic from the solar system's formation 4.6 billion years ago. At that time, a massive rotating disk of gas and dust collapsed under gravity. Conservation of angular momentum caused this disk to flatten progressively. Ultimately, the Sun formed at its center, while planets and other celestial bodies formed within the disk. Thus, the ecliptic plane became the primary reference plane for the solar system. The orbits of all planets are nearly aligned within this plane. However, interstellar visitors from beyond our solar system theoretically possess completely random orbital inclinations. Originating from all directions within the Milky Way, their home galaxies each have distinct reference planes. Thus, when these interstellar objects enter our solar system, they should cross the ecliptic plane at arbitrary angles. The probability of their orbits closely aligning with the ecliptic is extremely low. Calculations indicate this probability is only about 1 in 500. The arrival of 3I Atlas shattered this expectation. Its orbital inclination was measured at 175 degrees. This indicates it actually moves retrograde, in the opposite direction to planetary orbits. But more significantly, its orbital plane deviates only 5 degrees from the solar system's ecliptic plane. It aligns almost perfectly. This represents the first statistically improbable event. Even more astonishing is its specific trajectory. 3I Atlas did not merely traverse the outer reaches of the solar system. Its trajectory meticulously navigated the inner solar system, making close encounters with 3 planets: Mars, Venus, and Jupiter. Such multiple planetary close encounters are not mere geometric coincidences. They require precise timing, as each planet orbits at a different speed, along its own independent path. Let us examine these encounters closely. On October 3, 2025, 3I Atlas will fly past Mars at a distance of 0.19 astronomical units, approximately 18 million miles. This proximity is close enough that NASA will attempt to image it using the high-resolution camera on the Mars Reconnaissance Orbiter. Then, in November, it will skim past Venus at 0.65 astronomical units, about 60 million miles, before reaching its closest approach to Earth in December. At 18 cents, about 170 million miles. Finally, in March 2026, it will pass Jupiter at 36 cents, about 33 million miles. Any object traversing the solar system will intersect planetary orbits at certain points along its path. But what makes 3I Atlas unique is that, as it approaches each intersection, the corresponding planet happens to be positioned in that region. Considering Mars' orbital period is 687 Earth days, Venus is 225 days, and Jupiter's requires 12 years. Such temporal synchronization is exceedingly rare. Avi Loeb and his colleagues calculated the probability of these multiple encounters. They found the odds of 3I Atlas achieving close approaches to Mars, Venus, and Jupiter, all within a single flyby, is approximately 1 in 20,000. This figure represents pure chance, equivalent to rolling the same number on a die multiple times in succession. In statistics, when multiple low-probability events occur simultaneously, we begin to suspect it's more than mere luck. Loeb used a vivid analogy. If you saw someone roll doubles 10 times in a row at a casino, you might suspect the dice were loaded. While theoretically possible through pure randomness, the likelihood is minuscule. The prudent approach would be to inspect the dice for tampering. 3I Atlas's trajectory represents such a series of extraordinary dice rolls. Aligning with the ecliptic plane alone is improbable. Combined with close encounters with 3 inner planets, the multiplied probability of these independent events yields an extremely small composite probability. This unusual trajectory pattern prompts deeper reflection. if this object isn't random interstellar debris, but a probe guided by some form of intelligence. Then choosing such a path makes perfect sense. A meticulously designed trajectory maximizes scientific returns. Observing multiple planetary systems in a single flight, especially those like Earth where life might exist. From an engineering perspective, such a trajectory is highly efficient. By utilizing planetary gravity assists, a probe can adjust its velocity and direction with minimal fuel expenditure to achieve multi-target exploration. This is precisely the technique we humans frequently employ in designing outer solar system probes. Of course, we must maintain scientific caution. The universe is sufficiently ancient and vast that even extremely improbable events occasionally occur. This is the so-called inevitability on sufficiently long timescales. Perhaps we have merely witnessed a statistical marvel, a true random anomaly, but the essence of the scientific method lies in not being satisfied with attributing highly anomalous phenomena to mere coincidence, but instead proposing testable hypotheses and predictions. For 3I Atlas, this unusual orbital characteristic, combined with its anomalous mass and chemical composition, collectively form a pattern demanding serious interpretation. As we look ahead to future interstellar object research, 3I Atlas's trajectory reminds us the cosmos may be far more complex and fascinating than we imagine. It challenges us to maintain an open mind, while upholding rigorous scientific standards, to navigate the delicate balance between extraordinary claims and extraordinary evidence. This seemingly improbable path may ultimately lead us to a deeper understanding of the universe. Whether 3I Atlas is a marvel of nature or something else entirely, it has already transformed how we perceive interstellar space. In a comet's life, perihelion is a defining moment. It refers to the point in its orbit where the comet comes closest to the Sun. For 3I Atlas, this point lies inside Mars' orbit, approximately 1.36 astronomical units from the Sun. As the comet hurtles toward perihelion, the Sun's radiant heat intensifies dramatically, like an invisible hand, violently stripping away the comet's icy surface. These icy layers instantly sublimate from solid to gas, forming spectacular jets, carrying away vast amounts of dust and particles. This process is called sublimation, marking the comet's most active and intense phase. Near perihelion, the comet reveals its truest self. Its core structure faces its most severe test. Internal materials are exposed. Chemical composition is thoroughly analyzed. The comet's tail becomes longest and brightest. Activity levels reach their peak. Thus, for astronomers, observing a comet's perihelion passage is like reading its most private diary. It reveals the environment of its birthplace, its age, and even its ultimate fate. Yet for 3I Atlas, this crucial diary has been ingeniously closed by the cosmos at its scheduled perihelion moment. In October 2025, Earth will precisely occupy the opposite side of the Sun. From our perspective, 3I Atlas will be almost entirely concealed behind the Sun's blinding glare. This astronomical phenomenon is known as a solar conjunction. During this period, the Sun's powerful electromagnetic radiation and particle streams overwhelmed any faint signals emanating from its direction. Ground-based telescopes were rendered completely incapable of observation. Even space telescopes like Hubble or James Webb struggled to function due to the Sun's intense interference. This observational blind spot persisted for a full 3 weeks, from mid-October through early November, precisely the period when the 3I Atlas should have been most active. The probability of such a temporal coincidence has been estimated at between 1 in 20 and 1 in 30. Viewed in isolation, this probability is not negligible. Yet, when superimposed upon the numerous anomalies already associated with 3I Atlas, it becomes yet another thought-provoking coincidence. Professor Avilab refers to this phenomenon as a concealed vantage point. If an object seeks to execute certain operations undetected, there exists no more opportune time or location. The most significant implication of this concealed window lies in its potential to mask a maneuver known as the reverse Oberth effect. The Oberth effect is a fundamental principle of spaceflight dynamics, describing how a spacecraft can most efficiently alter its orbital energy by applying thrust at the point of maximum gravitational pull. Simply put, when approaching a massive celestial body at high speed, such as the Sun, igniting engines at this moment allows minimal thrust to yield substantial velocity changes. Human-launched probes frequently utilize the forward Oberth effect by firing engines near planets to accelerate and reach distant targets with less fuel. The reverse Oberth effect operates precisely the opposite. It involves firing engines at high speed to decelerate and harness the celestial body's gravity to facilitate capture. This transforms an escape-capable open hyperbolic orbit into a bound-closed elliptical orbit. For the 3I Atlas, perihelion is the ideal location to execute such a maneuver. If deceleration occurred at that point, direct observation from Earth would be entirely impossible. Only weeks later, when it re-emerges from behind the Sun, can we detect minute deviations from pure gravitational predictions by precisely calculating its new orbit. By mid-November, when 3I Atlas re-entered observable range, preliminary data suggested it remained in a hyperbolic trajectory, not captured by the Sun. However, this does not entirely rule out the possibility of a minor orbital correction. Precise orbit determination requires months of accumulated data. Extremely subtle velocity changes may necessitate a long observation baseline for reliable detection. The European Space Agency's Jupiter Icy Moons Explorer, JUICE, was en route to Jupiter at the time. It occupied a relatively unique observational vantage point, continuously monitoring 3I Atlas throughout November. A full analysis of this data won't be complete until early 2026. It may reveal whether anything unusual occurred during that 3-week period of silence. This uncertainty, this gap between the known and the unknown, is precisely the most frustrating yet captivating aspect of scientific exploration. The data we possess confirms 3I Atlas safely passed perihelion, yet insufficient to definitively rule out any anomalous behavior during that period. This state of unresolved uncertainty provides fertile ground for rigorous hypotheses and cautious speculation. If 3I Atlas is indeed an engineered artifact, then choosing to perform orbital adjustments behind the Sun at perihelion would represent a masterstroke of tactical strategy. This aligns with any engineering logic prioritizing efficiency and stealth, harnessing peak gravitational forces for maximum energy transfer efficiency, while leveraging a natural barrier to shield itself from potential observers. Of course, we must never mistake possibility for proof. All current discussions regarding its artificial manipulation remain purely speculative. Yet the existence of this concealed window undoubtedly adds another profound layer to the enigmatic dossier of 3I Atlas. It reminds us that the cosmos is not only vaster than we can imagine, but may also be more complex and subtle than we can conceive. What we perceive from Earth may merely represent the most superficial layer of the story. When 3I Atlas fully emerged from the Sun's glare in early December and reappeared clearly within telescopes' fields of view, Astronomers worldwide eagerly sought to determine whether it remained the object we previously knew, or whether, behind the scenes during those 3 weeks, certain pivotal chapters had been quietly rewritten. The answers lie concealed within forthcoming observational data, awaiting our interpretation. When 3I Atlas plunged into the inner solar system, it instantly became the focal point of global astronomical networks, from Earth's giant telescopes to orbiting space observatories. Countless precision instruments trained on this interstellar visitor, seeking to unveil its mysteries. The Hubble Space Telescope captured its first high-resolution images in early July. The images revealed a teardrop-shaped dust envelope, enveloping the central nucleus. Simultaneously, a faint dust tail extended away from the Sun. This is a classic feature of cometary activity. Solar radiation pressure pushes tiny dust particles outward, forming the comet's tail we observe. However, upon closer examination of the Hubble images, researchers noticed an unusual detail. On the solar side of the coma, a faint extension appeared. Such a solar extension is extremely rare in traditional comets, as cometary tails typically point away from the Sun. NASA scientists quickly offered an explanation. They suggested this might be an illusion caused by motion blur. When telescopes track a rapidly moving celestial object, if the exposure time is too long, the object's motion creates a trail in the image. Considering 3I Atlas was hurtling toward the Sun at tens of kilometers per second, this explanation seemed quite plausible. Most astronomers accepted this explanation. Motion blur is a common phenomenon in astronomical imaging, especially when observing fast-moving objects within the solar system. This minor anomaly was quickly filed away as a technical issue, but by late August, new images captured by Chile's Gemini South telescope revealed a change in circumstances. By this point, 3I Atlas had drawn closer to the Sun. The images clearly showed a normal dust tail, pointing away from the Sun. Scientists announced this indicated 3I Atlas was exhibiting characteristics consistent with a natural comet. However, the timeline raises an intriguing question. During the first 6 weeks after discovery, 3I Atlas displayed blurred visual features, unusual brightness, unclear tail structure, along with that perplexing solar extension. Yet, just after crossing Mars' orbit, as solar heating intensified, it began resembling a traditional comet. Abelaub cautiously suggests that surface appearance alone may not reveal internal structure. An engineered object traversing interstellar space for millions of years accumulates cosmic dust, icy particles, and volatile compounds on its surface. These materials, when heated by the Sun, be indistinguishable from a natural comet's surface. October's most compelling observations came from Mars. NASA's Mars Reconnaissance Orbiter reoriented its high-resolution imaging science instrument. This camera, typically used to capture Martian surface details, turned instead toward 3I Atlas, tens of millions of kilometers away. These images reveal a diffuse, nearly circular coma, enveloping a brighter central region. The nucleus itself appears as an elongated bright concentration. Resolution at that distance is approximately 30 kilometers per pixel. For an object with an estimated nucleus diameter of 5 to 10 kilometers, this means the solid core may occupy only a single pixel in the image. The official statement emphasized this as a technical achievement, marking the first direct imaging of an interstellar object's nucleus from another planet, while cautiously noting the image showed no features inconsistent with natural comet structures, no geometric shapes, no habeas artificial undecastions. However, careful analysis revealed a subtle anomaly. The brightest region of the coma was not centered on the nucleus. but offset by approximately 50 kilometers toward the Sun, though this equates to merely 1.5 pixels in the image. This measured asymmetry warrants attention. In typical comets, the coma produced by outgassing is densest near the nucleus, then gradually expands outward. Typically, brightness peaks at the central solid body and diminishes with increasing distance. High-resolution images reveal subtle differences. The brightest coma region is offset from the nucleus by about 50 kilometers, toward the sunward side. Several natural explanations are possible. Material outflows may preferentially erupt from the sunlit hemisphere, creating a denser concentration of dust and gas there. Rotation could carry active regions into sunlight, producing periodic outbursts that create the asymmetric distribution. Alternatively, the nucleus itself may have fragmented, with distances between fragments matching the observed offset. Yet another interpretation exists. If the nucleus is enveloped by a thin shell of material, perhaps a hollow structure, where only the outer surface responds to solar heating, then outgassing originates from that shell, rather than the solid core, depending on the shell's thickness and how sunlight penetrates it. You might observe this offset between where the brightness appears and the actual location of the solid structure. This isn't definitive proof. It hardly qualifies as an anomaly, more a curiosity, something that doesn't quite fit the standard model. But it doesn't explicitly contradict it either. The James Webb Space Telescope's infrared observations provide another crucial perspective. It measures the surface temperature distribution. The heating pattern of a solid, rocky object differs from that of a fluffy ice dust aggregate. The thermal response of a thin-walled hollow shell also differs from that of a solid body. Webb's preliminary data indicate that 3I Atlas's thermal signature aligns with a porous ice dust mixture. However, this does not rule out other possibilities. A properly designed shell, covered with natural cometary material, could precisely mimic this thermal behavior. All these observations collectively paint a complex picture. 3I Atlas looks very much like a comet, behaves largely like a comet, yet harbors subtle, persistent anomalies in the details. Each anomaly could be explained individually, but collectively they form a pattern, prompting scientists to keep asking questions. As we enter December's prime observation window, answers to these questions may become clearer, or this interstellar visitor may choose to keep its secrets on its journey back into interstellar space, leaving only more tantalizing clues behind. As 3I Atlas approached the Sun, its chemical composition gradually revealed itself through spectral analysis. Spectroscopy, a technique that identifies chemical elements by analyzing emitted light, acts like a cosmic barcode reader. Observations from the James Webb Space Telescope delivered the first surprise. 3I Atlas released an unusually high proportion of carbon dioxide, roughly 8 times that of water ice. Such a high ratio is highly unusual among comets in our solar system. Most comets are dominated by water ice. This discovery hints at a possible formation environment. Carbon dioxide ice is more stable than water ice at extremely low temperatures. This suggests 3I Atlas may have formed in the distant outer reaches of its parent galaxy, an extremely cold region. Another possibility is that it is exceptionally ancient, formed during a period when the Milky Way's chemical composition differed. The Very Large Telescope delivered an even more puzzling discovery in late August. It detected atomic nickel vapor in the comet's coma spectrum, emitting at a rate of approximately 4.6 grams per second. Nickel in comets is not unprecedented. It has been detected in some solar system comets and in the interstellar comet 2I/Borisov. What's truly peculiar is the apparent absence of iron. In nearly all comets documented, nickel and iron appear in roughly equal proportions. This makes sense cosmochemically. Nickel and iron form together in supernova explosions, travel through interstellar space together, and co-occur in primordial solar system material. Finding one without the other is like detecting smoke without heat. Not impossible, but suggesting unusual circumstances. Several explanations have been proposed for this discrepancy. Perhaps iron is present but undetected, due to specific conditions within the coma: temperature, density, radiation environment. Perhaps iron is locked in compounds that resist decomposition, unlike nickel-bearing materials, or observational sensitivity limitations prevent detection at the required level. Another possibility is that 3I Atlas formed within an environment with an anomalous metallicity compared to typical solar system chemistry. Its parent star may have possessed distinct elemental abundances, reflecting the unique formation history of that region within the Milky Way. Then there is the issue of carbon chain depletion. 3I Atlas exhibits unusually low levels of 2-carbon and 3-carbon molecules that typically produce the green fluorescence common in comets. However, during a total lunar eclipse in early September, when sky conditions were exceptionally dark, images captured by astrophotographers revealed 3I Atlas emitting a distinct green glow. If the expected carbon chain depletion, then where does the green come from? Could originate from cyanide, whose concentration the Very Large Telescope detected increasing. It could stem from buried material eventually exposed as the surface sublimates. Could arise from chemical processes we don't fully understand, occurring under the specific conditions experienced by this object. Each chemical anomaly could be addressed individually, but a pattern begins to emerge: mass higher than expected, trajectory abnormally aligned, chemical signature slightly deviating from standard profiles, visual features developing in unexpected sequences. Together, these characteristics create what Rob describes as a persistent sense of strangeness, a strangeness worthy of continued scrutiny, even as most scientists reasonably conclude the object is natural. It is crucial to remember that consistency does not equal proof. A technical object coated in ice dust releases the same molecules as a natural comet when heated by the sun. We detect water, carbon dioxide, organic compounds. Everything we currently observe lacks the ability to distinguish between surface frost and overall composition. We are like examining a beautifully wrapped gift. We can see the color and texture of the outer packaging. We might even detect faint scents emanating from the wrapping material. But we cannot know if the interior holds simple rock or an intricately engineered device unless we can penetrate the surface or the object chooses to unwrap itself. We may never ascertain its true nature. The chemical enigma of 3I Atlas reminds us that cosmic chemistry far exceeds our current understanding. Each new observation both answers questions and raises new ones. This is the very essence of scientific inquiry, and why studying this interstellar visitor is so captivating. When we compile all the anomalous data regarding 3I Atlas, a fundamental question becomes unavoidable. Is it an extraordinarily rare natural celestial body, or humanity's first encounter with extraterrestrial technology? The scientific community has divided into two camps, each drawing diametrically opposed conclusions from identical observational data. Scientists advocating for artificial origins present an argument grounded in multiple anomalous evidences. They contend that a single coincidence might be attributed to luck, but the convergence of so many low-probability features on a single object strongly suggests the possibility of underlying intent. The first and most central argument concerns mass anomaly. The minimum mass estimate of 3.3 billion tons makes it thousands of times heavier than any known interstellar object. The probability of such a massive, solid body forming naturally and being capable of interstellar travel is extremely low. However, if it were a hollow shell structure, such as a probe or spacecraft, this mass becomes plausible. Engineering principles dictate that long-distance vehicles often employ lightweight structures, gaining strength through geometric design rather than mass accumulation. All human-built long-range transport vehicles, from ships to spacecraft, follow this principle. The second argument concerns the trajectory's remarkable coincidence. 3I Atlas not only aligns nearly perfectly with the solar system's ecliptic plane, but also passes close to 3 inner planets during a single flyby. The combined probability of such a trajectory is approximately 1 in 20,000. More crucially, its perihelion timing coincides precisely with its position behind the Sun, creating a 3-week blind spot for Earth-based observation, if this object required orbital adjustments or system maintenance. Without detection, there could be no more perfect timing or location. The third argument concerns contradictory chemical signatures. Detected nickel vapor yet lacking iron elements. High proportions of carbon dioxide. Abnormal depletion of carbon chain molecules. While each of these features could find natural explanations, their combined pattern is unique among known comets. If this were a technological object, with a surface coated in ice and dust accumulated during interstellar travel, then its surface chemistry would exhibit this hybrid signature, reflecting its external journey, while concealing its internal nature. The fourth argument concerns the evolution of visual characteristics. During its initial discovery phase, 3I Atlas displayed indistinct features, including that perplexing solar extension. Only after penetrating the inner solar system did it develop a typical cometary appearance. This precisely aligns with the expected behavior of a technological object, as its surface coatings gradually activated under solar heating. However, the mainstream astronomical community remains skeptical. They propose a comprehensive natural explanatory framework, arguing we are witnessing a rare yet entirely natural cosmic phenomenon. Regarding the mass anomaly, they suggest our planetary formation models may be incomplete. Perhaps the number of large interstellar objects in the galaxy exceeds our current estimates. Alternatively, 3I Atlas may have formed within an exceptionally dense protoplanetary disk, where large celestial bodies are more readily formed. Statistically, rare events do occur. Humanity has only been searching for a decade, and may have coincidentally encountered that once-in-a-thousand-year sample. Regarding orbital coincidences, they point out that probability calculations themselves carry uncertainty. In a galaxy hosting hundreds of billions of stars, even events with extremely low probability are bound to occur somewhere, sometime. We perceive it as special, simply because we are the observers of these events. This is a form of selection bias. Regarding chemical anomalies, planetary scientists emphasize our limited understanding of chemical diversity in exoplanetary systems. Each stellar system possesses unique elemental abundances and thermodynamic histories. 3I Atlas may originate from such a chemically distinct system. Its characteristics challenge our models, yet this is precisely the significance of studying interstellar objects, expanding our knowledge of cosmic chemical diversity. Regarding the coincidence of observation timing, astronomers remind us, confirmation bias may be at play here. We notice all seemingly coincidental features, yet overlook thousands of unremarkable, ordinary ones. Moreover, statistically speaking, a 1 in 30 probability isn't particularly low. Among countless astronomical events, such temporal coincidences occur frequently. Both sides acknowledge gaps in the evidence. The artificial origin theory struggles to explain. Why would a technological object disguise itself as a comet, yet leave so many suspicious clues? If it sought concealment, why not choose a less conspicuous trajectory, or better mimic the chemical signatures of ordinary comets? The natural origin theory, meanwhile, struggles to explain why would all these anomalous features are so concentrated on a single object. While each anomaly can be explained individually, their combination becomes statistically increasingly improbable. This is precisely where scientific inquiry thrives. In the absence of conclusive evidence, both possibilities must remain open. Science does not choose preferred explanations. It follows where the evidence leads. For 3I Atlas, the evidence points in a distinct direction, an object of extreme anomaly. Yet this alone does not prove its artificial origin. Velen proposes a methodological approach. We should employ Bayesian reasoning to continually update our confidence levels as new evidence emerges, rather than clinging to preconceived positions. Within this framework, each anomalous feature of the 3I Atlas moderately increases the likelihood of artificial origin, though it has not yet reached conclusive levels. This scientific debate holds intrinsic value, as it compels us to re-examine fundamental assumptions, refining observational techniques, developing more sophisticated theoretical models, regardless of what the 3I Atlas ultimately proves to be. This debate has already propelled progress in astronomy. As we prepare for critical observations in December, both possibilities should remain in mind. If we seek only evidence supporting natural origins, we may overlook truly revolutionary discoveries. Conversely, if we interpret every anomaly as artificial evidence, we risk misreading nature's creativity. At this stage of exploration, maintaining a cautiously open mindset may be the most scientific stance. The universe may generate patterns we deem anomalous through natural processes, or other intelligences we have yet to encounter may indeed exist. The true significance of the 3I Atlas may not lie in immediately answering this question, but in teaching us how to better pose it. In the debate surrounding the 3I Atlas, Harvard astronomer Professor Avi Loeb proposed a systematic analytical approach. He advocates using statistics and probability theory to evaluate such anomalous celestial bodies, rather than relying on intuition or preconceived notions. Loeb's method begins with a fundamental principle. When analyzing unknown celestial bodies, we should compare the relative likelihood of two hypotheses, one being entirely natural origins, the other being possible artificial origins. By evaluating the probability of various observational features occurring under both hypotheses, we can calculate Bayesian probabilities and objectively determine which explanation is more plausible. For the 3I Atlas, Loeb's team identified 7 significant anomalous characteristics: abnormally massive, high alignment with the ecliptic plane, orbits intersecting multiple planets at close proximity, synchronized perihelion timing with solar conjunction, abnormal nickel-iron ratio, high carbon dioxide proportion, and atypical morphology in early observations. They estimated the probability of each feature occurring under natural assumptions, and then multiplied these probabilities. The resulting composite probability was extremely small, on the order of 1 in 10 million to 1 in 100 million. Such a minuscule probability implies that if our cosmological models are correct, the likelihood of discovering such a celestial body within such a short observation period is virtually zero. This leads to two inferences. Either our cosmological model severely underestimates the number of large interstellar objects, or 3I Atlas is not a randomly distributed natural object. Loeb argues that based on existing astrophysical formation theories, the first explanation faces significant difficulties. Therefore, the second explanation warrants serious consideration. To systematize this approach, Loeb proposed an anomaly scale, a scoring system ranging from 0 to 10. A score of 0 indicates complete conformity with known natural celestial bodies. A score of 10 signifies conclusive evidence of artificial origin. Intermediate scores denote varying degrees of anomalous characteristics. On this scale, typical solar system comets and asteroids receive a score of 0. Oumuamua, due to its unusual shape and acceleration, is rated 3. Borisov, sharing chemical composition with solar system comets, is rated 1. Meanwhile, 3I Atlas, based on its multiple anomalous characteristics, has been preliminarily rated between 5 and 6 points. The significance of this rating system lies in providing a standardized framework for evaluating interstellar objects. When an object's rating exceeds a specific threshold, such as 5 points, it should trigger an internationally coordinated enhanced observation program, rather than being easily dismissed. However, this quantitative approach has sparked intense debate within the scientific community. Many mainstream astronomers strongly oppose this evaluation framework. They contend that assigning numerical values to ambiguous observational features creates a false sense of precision. Astronomical observations inherently involve uncertainty. Quantifying anomaly levels with specific numbers may mislead the public and policymakers. More fundamental objections pertain to scientific philosophy. Traditional scientific methodology adheres to Occam's razor principle. When confronted with anomalous phenomena, the simplest explanation should be favored. For the 3I Atlas, the simplest explanation remains natural origin, even if it represents a natural phenomenon we do not yet fully comprehend. This internal scientific disagreement reflects deeper cognitive divergences. One camp asserts science should boldly explore all possibilities, even when they challenge established beliefs. The other emphasizes scientific rigor and conservatism, avoiding premature acceptance of extraordinary claims. This tension is a recurring theme in scientific history, from Copernicus's heliocentric model to plate tectonics. Revolutionary scientific ideas often take decades to gain acceptance. Loeb believes we may now be at another such turning point. The study of interstellar celestial bodies is opening a new scientific frontier. The value of statistical probability analysis lies in its ability to quantify intuition. When multiple astronomers examine the 3I Atlas data, they may intuitively react with "this is unusual." Probability analysis attempts to translate this intuition into testable hypotheses. For instance, if we accept Loeb's assessment that the 3I Atlas has a 1% probability of being artificial, is this probability high enough to justify significant resources for further investigation? Different scientists will offer differing answers, but it at least provides a rational basis for discussion. With next-generation observatories like the Vera Rubin Observatory coming online, we will discover more interstellar objects in the coming years, making statistical evaluation methods increasingly crucial. We must decide how to allocate limited observational resources. Should we study every new interstellar object discovered, or concentrate resources on the most anomalous ones? The case of 3I Atlas compels us to confront these questions. regardless of its ultimate nature, this debate has already driven methodological progress. It teaches us how to question more systematically, how to make reasonable judgments with limited evidence, and how to balance scientific conservatism with exploratory spirit. If 3I Atlas is indeed an artificial construct, it will force us to confront a deeper question. What is the nature of intelligent civilizations in the cosmos? How would they treat one another? A renowned conceptual framework for this question is the dark forest hypothesis, popularized by Chinese sci-fi author Liu Cixin. Yet its intellectual roots trace back to early game theory and cosmological sociology. The hypothesis's core premise is profoundly thought-provoking. The universe may teem with intelligent civilizations, yet all choose silence and concealment. The hypothesis's logic rests on two fundamental axioms. First, survival is a civilization's primary imperative. Second, civilizations tend to grow and expand. Yet the total amount of matter in the universe remains largely constant. From these two axioms, some unsettling conclusions can be drawn. No civilization can ascertain the intentions of others. They may be peaceful or hostile. More critically, civilizations cannot determine each other's technological level. A seemingly friendly signal could originate from a civilization far more technologically advanced. Under such profound uncertainty, the safest strategy is to remain silent, refrain from transmitting signals that reveal one's position, and avoid responding to any detected signals. Much like in a dark forest, where every hunter lurks in the shadows, the first to make a sound risks becoming prey to others. More radically, if a civilization does detect another's presence, the rational choice might be to preemptively eliminate the potential threat, rather than risk waiting for a possible attack. This hypothesis offers a possible solution to the Fermi paradox. If numerous intelligent civilizations could exist in the universe, why do we see no obvious evidence of their presence? Perhaps the answer lies in those civilizations that revealed themselves, being unable to survive long enough to become conspicuous. Applying the dark forest hypothesis to the 3I Atlas yields a series of thought-provoking scenarios. If it is a detector, what might its mission be? One possibility is a reconnaissance mission, systematically surveying star systems within the Milky Way, searching for planets potentially harboring life, and assessing the technological level of other civilizations. Such a probe might be designed for maximum stealth, to avoid alerting any indigenous civilizations that might exist. Another possibility is a communication relay station, transmitting messages between star systems. If its creators wish to conceal the location of their homeworld, they might employ such a mobile relay station, rather than a fixed signal transmitter. A third possibility is a dormant archive, carrying the complete knowledge of a civilization, launched when its homeworld faced destruction, to serve as a seed for civilization, drifting through space awaiting the right moment to activate. The most unsettling possibility is that the probe itself is a weapon system, autonomously assessing potential threats and acting according to pre-programmed protocols. While this scenario is purely speculative scientifically, cannot be entirely ruled out logically. Even disregarding these extreme scenarios, the very existence of 3I Atlas would transform our understanding of the cosmos. If it is indeed an artifact, it would prove that at least one extraterrestrial civilization has attained the technological capability for interstellar travel. Moreover, their decision to send probes into space, regardless of their specific mission, implies that technologically advanced civilizations may not be rare in the universe. According to estimates from the Drake equation, if civilizations emerge with sufficient frequency, multiple technological civilizations could coexist within the Milky Way, even if all adhere to the dark forest principle by remaining concealed. Their probes might still occasionally encounter one another. The Three-Eye Atlas also prompts us to reflect on humanity's own actions. For years, we have actively broadcast signals into the cosmos. The Voyager Golden Records, the Arecibo message, within the framework of the dark forest. These actions may appear remarkably naive. From an astronomical perspective, the dark forest hypothesis remains merely a thought experiment, with no direct evidence for or against it. Yet the anomalous characteristics of Three-Eye Atlas at least provide grounds for seriously contemplating these deeper questions. Regardless of what Three-Eye Atlas ultimately proves to be, it has already accomplished a vital mission, forcing us to transcend traditional astronomical thinking, linking planetary science, astrophysics, and cosmic sociology. It reminds us that the universe may be far more complex than we imagined, abounding in natural wonders, while potentially harboring traces of other intelligent beings. In the coming observations, we will continue seeking answers, but perhaps the greatest revelation has already emerged. As we gaze upon the stars, other eyes may be watching us, and the rules of this cosmic dark forest game we are only just beginning to understand. As Three-Eye Atlas approaches Earth in December 2025, the global astronomical community is meticulously preparing for an unprecedented collaborative observation. This close encounter will offer the prime opportunity to study this interstellar visitor, and may well be the last. During a 10-day window in mid-December, Three-Eye Atlas will reach its closest point to Earth, at a distance of approximately 180 million kilometers. Though too distant for naked eye observation, this distance presents an exceptional research opportunity for professional telescopes. The Global Observation Network stands ready. The Hubble Space Telescope will conduct continuous monitoring, capturing the highest resolution visible light imagery. The James Webb Space Telescope will activate its powerful infrared instruments to analyze the object's thermal radiation properties. The Chandra X-ray Observatory will search for potential high-energy radiation signals. Ground-based observations are equally vital. Chile's Very Large Telescope will employ adaptive optics to compensate for atmospheric turbulence and yield sharper images. Hawaii's Keck Telescope will conduct spectral analysis. America's Green Bank Telescope will monitor for possible radio signals. These observations will span the entire spectrum from radio waves to gamma rays. Each wavelength band reveals distinct information. Visible light images show surface features and shape. Infrared data reflects temperature distribution and composition. Ultraviolet observations track gas release processes. Radio measurements may detect artificial signals. Scientists anticipate answering several key questions. First are precise orbital parameters. High-precision measurements using long baselines will determine whether Three-Eye Atlas performs minor orbital corrections. During perihelion, even velocity changes of a few meters per second will manifest in the data. Second is surface feature analysis. Optimal resolution may reach hundreds of meters per pixel, revealing whether the nucleus is a single structure or fragmented. It will show if the surface has impact craters or geological features, and whether any geometric regularities exist. Color variations may indicate compositional differences. Thermal property measurements are particularly crucial. Infrared data from the Webb telescope will show how Three-Eye Atlas responds to solar radiation. A solid rock body heats differently from a porous structure or hollow shell. Thermal inertia data will help distinguish these possibilities. Gas release behavior is also closely monitored. Spectrometers will track emission rates of various molecules. including water, carbon monoxide, carbon dioxide, and cyanides. Natural comets exhibit predictable gas release patterns. Any anomalous variations may suggest unusual internal structures. Rotational state serves as another critical indicator. By measuring brightness variation cycles, 3I Atlas's spin rate can be determined. Natural bodies typically maintain stable rotation, while engineered objects may display unnatural rotational characteristics. The uniqueness of this observation lies in it being our final opportunity to acquire high-quality data. After this, 3I Atlas will rapidly recede. Both brightness and resolution will sharply decline. By early 2026, only the largest telescopes will still be able to track it. Within a few years, it will vanish entirely from observational range. Analysis of observational data will commence immediately, but full comprehension may take months. Preliminary findings will be released within weeks. Detailed scientific papers will require 6 months to a year. The international team will share data for independent analysis, then compare results to seek consensus. This encounter is not merely a scientific observation, but a practical exercise in humanity's understanding of the cosmos. How we confront the unknown, how we collaborate in exploration, how we interpret anomalies, all will accumulate experience for future interstellar encounters. The emergence of 3I Atlas reveals a critical issue. Significant institutional gaps exist within the international community regarding responses to potentially artificial interstellar objects. Currently, no international organization is specifically tasked with assessing interstellar objects that may exhibit technological characteristics. NASA tracks near-Earth objects to mitigate collision risks. Space agencies collaborate on planetary defense. SETI organizations search for radio signals from distant stars. Yet, potentially artificial objects physically traversing the solar system remain in a regulatory vacuum. This institutional absence leads to inefficient responses. When 3I Atlas was discovered, observational recommendations relied on individual scientists' initiatives. Telescope time was requested through conventional channels. Data remained fragmented across research groups, hindering integration. No mechanism ensured comprehensive, systematic investigation. Avi Loeb proposed establishing a dedicated international body. This agency would undertake several critical functions: rapidly assess newly discovered interstellar objects, allocate observational resources based on anomaly severity, coordinate global telescope observation schedules, establish standardized data analysis protocols, develop guidelines for information release and public communication. However, this proposal faces numerous challenges. Funding sources remain unclear. Member state participation is uncertain. Political considerations may influence scientific decisions. Defining level of abnormality is contentious. What evidence warrants elevated investigation levels? All require international consensus. The dissemination of scientific information also presents problems. Specialized papers are overly technical. Media reports often oversimplify. The public receives fragmented information. They either perceive scientists as overreacting or fear an imminent alien invasion. This gap in understanding carries serious consequences. On one hand, truly significant discoveries may be missed because the public and politicians fail to grasp their significance. On the other hand, unnecessary panic may be triggered. When information is opaque, rumors fill the void. The case of 3I Atlas is particularly illustrative. Internal scientific debates were simplified to: Harvard professor claims it's an alien spacecraft. NASA scientist insists it's just a comet. Complex scientific evidence and probability assessments. were compressed into binary headlines. Establishing a systematic evaluation framework is urgent. With the Vera Rubin Observatory now operational, discoveries of interstellar objects will become frequent. We may discover several such visitors annually. Most will indeed be ordinary comets and asteroids, but occasionally anomalous cases like 3I Atlas will emerge. An ideal framework should incorporate several elements: clear evaluation criteria and trigger conditions, an international platform for data sharing, mechanisms for rapid mobilization of observational resources, progressive response protocols, a professional public communication team. This framework must address not only scientific questions, but also societal implications: how to maintain transparency while avoiding panic, how to balance scientific exploration with public safety, how to preserve national interests within international cooperation. Public scientific literacy must also be elevated. More people need to understand. Science is an ongoing process of exploration. Uncertainty is a normal part of it. Extraordinary claims require extraordinary evidence. But extraordinary evidence requires diligent seeking. The 3I Atlas leaves us with this insight: the universe may be far more complex than we imagined. We must neither blindly assume every anomaly is an alien signal, nor stubbornly reject non-traditional explanations. Finding balance between caution and openness will be key to future interstellar exploration. Establishing essential institutional and cognitive frameworks is not only for responding to the 3I Atlas, but also for preparing for inevitable future discoveries. When the next interstellar visitor arrives, we should be better prepared. The emergence of the 3I Atlas poses profound challenges to modern scientific methodology. It compels us to re-examine the applicability of fundamental principles under extreme conditions. Occam's razor has long guided scientific inquiry. This principle holds that when faced with multiple explanations, the simplest is often the most likely to be correct. For most astronomical phenomena, this remains an effective guiding principle. Yet the 3I Atlas reveals that in highly anomalous circumstances, blindly applying Occam's razor may prove problematic. The simplest explanation is not always the most accurate, especially when confronting entirely novel phenomena. The universe is 13.8 billion years old. The Milky Way contains hundreds of billions of stars. On such vast space-time scales, events we deem extremely anomalous may actually occur with some frequency, or there may exist natural processes we have yet to recognize. Scientific history is replete with such examples. When physicists first observed quantum entanglement, Einstein called it spooky action at a distance, believing it violated the simple principle of local realism. Yet subsequent experiments proved quantum entanglement to be real. We must accept this more complex reality. The 3I Atlas may well represent such a turning point. It demands we find a new equilibrium between simplicity and completeness, not by abandoning Occam's razor, but by defining true simplicity with greater care. Another critical question is balancing two risks: the risk of making extraordinary claims versus the risk of missing extraordinary discoveries. The scientific community has traditionally prioritized the first risk, fearing that premature acceptance of revolutionary ideas could damage scientific credibility. This caution is justified in most cases, preventing the proliferation of pseudoscience. But as our exploration capabilities grow, the cost of the second risk is rising. If we miss evidence of extraterrestrial technology due to excessive caution, the cost could be immeasurable. The 3I Atlas teaches us the need to balance openness with skepticism. We should remain open to all possibilities, while upholding rigorous standards of evidence. This methodological shift is embodied in Rob's anomaly scale, which provides a progressive evaluation framework that avoids binary all-or-nothing judgments. It allows us to rationally allocate research resources until conclusive evidence emerges. The 3-eye atlas also highlights a fundamental limitation in scientific inquiry. Astronomy is inherently observational, not experimental. We can only passively observe phenomena as the universe presents them, and cannot actively design experiments to test hypotheses. For interstellar objects, this limitation is particularly acute. We have only one chance to observe them, and cannot request a repeat flyby for further study. This irreproducibility demands that we collect as complete a dataset as possible on the first encounter. With the Vera Rubin Observatory now operational, we stand at the threshold of a new era, where interstellar object research will shift from case-by-case discoveries to systematic surveys. Within the next decade, we may discover dozens or even hundreds of interstellar visitors. Most will be small, ordinary icy rock mixtures, yet more anomalous samples are bound to emerge. The value of 3-eye atlas lies in providing us with the first practical case study for handling such anomalies. It compels us to develop new observational strategies, new data analysis methods, new theoretical models, and new models of international collaboration. This new era of astronomy demands a more flexible mindset, one capable of simultaneously considering multiple possibilities, both natural and artificial, without prematurely ruling out any reasonable hypothesis. It also demands we rethink how science is communicated, how to maintain scientific rigor while accurately conveying uncertainty to the public, how to cultivate public understanding of the scientific process, rather than merely accepting scientific conclusions. The ultimate legacy of the 3-eye atlas may not be solving its own mystery, but propelling us to refine how we explore the cosmos. It reminds us to maintain humility, acknowledging the limitations of existing knowledge, while preserving the courage to follow evidence wherever it leads. In future interstellar exploration, we need both traditional rigor and open imagination. The combination of these qualities will guide us toward deeper discoveries. Whatever the 3-eye atlas ultimately proves to be, it has forever changed how we view the cosmos and how we position ourselves within it. This is its most enduring revelation to science.